Assalamu alaikum. Dear learners, I hope you are fine and doing great. In today's video, I am going to explain you that how you can model a simple pendulum in MATLAB. We are going to model this pendulum using three different systems. Firstly, we are going to model it using its differential equation, which is written over here. And additionally, we are going to calculate its kinetic energy and potential energy, and we are going to add them up to get the total energy. So after this implementation, we are going to use Simscape blocks to model the physical system of this pendulum. Then thirdly, we are going to model this pendulum using Simscape Multibody blocks, and we are going to see the pendulum in motion on Mechanics Explorer. Additionally, I am going to model this pendulum under both conditions, that is the ideal and the non-ideal one. In one case, that is the ideal, we are not going to consider any damping effects or the energy loss elements. But in the second, we are also going to add some damping effects to model the energy loss, and we will see that how the pendulum swings and then stops. So let's start. On this diagram, you can see that the pendulum is making an angle theta with the vertical, and at the shown point, the weight of the pendulum is mg, which is acting downwards. Right now, mg sine of theta is the force that will make the pendulum go back towards its equilibrium position, whereas mg cos of theta will be the component of the force responsible for the tension in the string. Driving its differential equation, we will arrive at this. Over here, the term b theta dot represents the damping effect. If we make b 0, then we can omit the viscous friction effects on the pendulum. So we are going to do both of the things. And then over here you can see that the kinetic energy can be calculated as half mv square, where v is the linear velocity. And using the string's length L and the angular velocity theta dot, we can figure out the linear velocity as L theta dot whole square, or as written L square theta dot square. And on the other hand, the potential energy is equals to mgl into 1 minus cos of theta. For an ideal case, the total energy, which is the sum of kinetic energy and potential energy, should remain the same. So we will calculate these energies and plot them to see what's happening. Okay, so let's start with the first way of modeling this pendulum, that is through the differential equation, which is shown over here. In the differential equation, you can see that the highest order derivative term which is available is theta double dot. So we will need two integrators. So I'm going to add two integrators. This is the first one and this is the second one. The output of the first integrator will be theta dot. So I'm labeling the wire as theta dot, and the output of the second will be theta. So I'm labeling it as theta. Let me take it over here and zoom it a bit. And the input of this first integrator block will be theta double dot. So I'm labeling it as theta double dot. Okay, so this differential equation says that sine of theta should be multiplied with mgl. So I'm going to provide this theta to sine function. I can take the sine function over here. I have rotated it and supplied it with theta. And then it should be multiplied with mgl. So I need a gain. Once again, I'm going to rotate it. Now the value of this gain should be mgl. Right now, I'll stop over here and define all the variables before proceeding. So I'm going to go to the modeling tab and then in Model Explorer. Inside this model, I have this model workspace, and over here I can define all the variables. So I'll need m, and its value I'm going to define is 0.2 kg, so that's why it's 0.2. Then L is the length of the string. I'm going to define it as 0.5. Then I'll need G, which is the gravity, so it will be 9.81. And I need B, the damping as well. I can make it currently, let it be 0, then we are going to change it later on. So I have defined all these variables in the model, and now I can use them over here. So M, G, and L. Okay, so sine of theta is being multiplied with MGL. I'll get this term. And if I take it on the other side, it will have a minus sign. And additionally, I'll take this term B theta dot on the other side as well. So I can get B theta dot from here. So all I have to do is I have to multiply this theta dot with a gain whose value is B. So over here, I'll be getting B theta dot. Okay, so now I have to add these two terms up. I can use a sum block, and I'm going to make it like this so that I'll have one minus sign at the top and one at the bottom. So both of these terms are, if taken on the other side, will have negative sign with them. That's why I have minus b theta dot minus mgl sine of theta. And this thing, if divided by ml square, will give me theta double dot, which is over here. So I'm going to use another gain. This time its value should be m into L square. So I've written MLL and I can provide it to the sum block and then I can connect it over here. So that's it. I have modeled this differential equation over here. Now all I need to do is I need to calculate these energies. So for kinetic energy, I need to model this equation, and for potential, this one. I'm going to use MATLAB function file to do that. So I'm going to insert MATLAB function, and this will require some inputs, which I'll configure later on. So inside this MATLAB function, I need three outputs. So if I click on this edit data, I can open these things. I can close the property inspector, and these are the inputs and the outputs. So this output y, it should be Ke, which is my kinetic energy. Then I need another output, which is Pe, and then total energy T. So these are my three outputs. You can configure them as output by clicking on this icon and selecting output data. And like this. So now all these three things are the output. And for the input, the first input I'll need, if I go back over here, you can see that I need M, I need L, I need theta dot, and I need theta over here. So all these things are needed by this function file to compute Ke, kinetic energy, and potential energy. M, L, and V, these are the variables already present in the model space. So I won't be providing those things to this function file. I only have to provide theta and theta dot. So that's why if I go in over here once again, I need theta. That will be my input. I need another input, which will be theta dot. And then I need three other inputs, which are M, G, and L. But these are not the inputs, these are parameters. So I'm converting these inputs to parameter data so that it can automatically pick it from the model workspace. Now I can write the equations over here. So for Ke, the equation was 0.5, that is 1 by 2, multiplied with M multiplied with L square multiplied with theta dot square. And for potential energy, the equation was M multiplied with G multiplied with L multiplied with 1 minus cos of theta. And the total energy was nothing but Ae plus Pe. That's it. Okay, so I have this function that can calculate all these energies. All I need to do is now supply it with theta and theta dot. Okay, so, to make these things a bit better, I should have theta dot at top and theta at the bottom. I can go in here and change the port number of theta to 2. Theta dot's port number will automatically change to 1. Okay, so now I have a much better view so that these lines don't overlap with each other. Okay, so now these energies are being calculated. Now I need to plot these things so that I can see what's happening. So I'm just going to terminate these signals and then I'm going to use data inspector with it. So I need three terminators. And for data inspector to show all these signals which I need this theta. So I'm clicking on this signal and I'm going to log this signal like this. I'm also going to log the kinetic energy, uh, the potential energy, and the total energy. It's better to label these signal wires so that the data inspector show you these the names of these signals. So I'm clicking on it and typing in Ke. Over here I can type in Pe, and over here I can type in Q. Okay, I guess that's everything. Now all I have to do is I have to give an initial angle to my pendulum. That initial angle can be given through this integrator because this integrator is producing theta. So initial angle will be, let's suppose in radians, it is 0.5. Okay. So now I'm going to go to the simulation tab and going to run this thing. I just realized that I made a mistake over here. When this MGL sine theta term will go on the other side and B theta dot term will go on the other side, this ML square will divide these two terms. But over here in the gain block, I have used ML square in the numerator, which is being multiplied with these things. So I have to go over here and then write 1 divided by this term. Okay, so now we are done and we can run the simulation for 10 seconds and see what happens. Okay, I've run it, and to see the logged results, I can click over here on any of these signals, or I can click on this data inspector. Okay, so this is the graph I am seeing, but I can see that I guess there are not many sample points in the simulation. So I'm going to close it and then go into the model settings. And in the solver details, I'm going to change this maximum step size to 0.001 and click OK. Now simulate it once again and open the data inspector. Now the graph looks quite smooth. So you can see that this is the graph for theta and it starts from zero point 0.5 radians. We gave this as the initial angle of the pendulum and it keeps on oscillating between plus zero point 0.5 and minus zero point 0.5. And it will keep on doing that because there was no damping, so there is no energy loss and the pendulum will keep on oscillating. You can go to, you can click over here and change the layout to this subplot and select this thing and plot all the energies over here. So I have plotted the kinetic energy. So this is the kinetic energy. You can see that at the very start, the pendulum is at rest. So it has zero kinetic energy, whereas the potential energy is maximum. So this orange line is showing the potential energy. You can change the color to look a bit different. I'm changing it to purple and also changing the thickness to 3. And for kinetic energy, you can do the same. So let's change its thickness to 3. So these are the energies. You can see that how beautifully the kinetic energy is changing or transforming into potential and the potential back into kinetic. So at the very start, the pendulum has the potential energy, but no kinetic energy. And then they start oscillating. And if I plot this total energy, let me make its width as 3 and plot it over here. You will see that it will be a flat line. So for an ideal pendulum case, the energy which you have provided because of the initial configuration or because of the initial angle, that energy is conserved and it remains a flat line. Okay, so now let's add damping effect. So I'm going to close it, go to the modeling, and in the model explorer, and in the model workspace, now I can make this be maybe 0.01. Let's see what effect this does. I've simulated it once again and I'll open the data inspector. And now you can see that the total energy is decreasing and the oscillations are dying out. But still, the pendulum is swinging. So we can increase the value of B a bit more so that we can see the drop in the kinetic energy a bit more quickly. I'm going to change it to 0.1. Now in the data inspector, now you can see that how the things are changing. Okay, so over here you can see that the energy has dropped almost to zero and the pendulum's oscillations have died out as well. Let me change this B once more to 0.4. I've changed B to 0.4 now. Let's see what happens now. Okay, so we can see that. Okay, so we can see that over here, the oscillations have died out almost after 6 seconds, and same is true for the energy. I guess it's working nicely. Okay, so this was one way of modeling the pendulum. Now let me show you another way. That is by using Simscape blocks, and you'll see that we don't have to model this differential equation. We can do it without that. So for Simscape, let me take it a bit over here. The very first thing is I need an inertia. So I'm going to insert inertia and I can place it over here. This inertia will be acted on by a torque. I need an ideal torque source. And the R port is connected to the inertia, whereas the other port, the C port, the case port, should be connected to the mechanical reference. So I can have rotational mechanical reference, and I can connect C over here. Furthermore, there is a damper between the inertia and the mechanical reference, so I can add a rotational damper as well. So that's it. And now uh, I guess that's everything I need to add. Now I just need to add the torque source over here, that what kind of source is acting on this inertia. Because we have modeled the pendulum as a point mass, so there is nothing else in our system. Okay, to provide this torque source, we have to measure the angle of this inertia, multiply it with sine of theta, and let me take you over here and to see that what kind of torque is acting on this pendulum bob. This is the force, which is mg sine of theta, multiplied with this L. That will be the torque acting on this pendulum bob, but in negative direction because it is taking you towards equilibrium position. So that's the torque we have to model. So how we can get theta over here? We can use a rotational sensor. So I'm going to insert a rotational motion sensor. Let me rotate it. I can now flip it so that I have the measurement ports on the other side. I can connect it over here and the other thing to the reference. Okay, so this rotational sensor is going to provide me the velocity, angular velocity, which is W, and angle, which is A of this inertia. And I can convert this angle and this angular velocity into Simulink signals. Right now, these are all physical system signals. So I can use the PS to Simulink converter. I need two of them. Now I can multiply this angle with sine and multiply this sine with a gain. This gain will be minus mg. So just to recap it, the force acting on this point, which is responsible for moving the pendulum in this direction, is mg sine of theta, multiplied with this moment arm L will give us the torque which is acting on this pendulum bob. So that's why we have modeled it as mgl sine of theta, but with a negative sign so that it takes it back towards equilibrium position. So this is the torque which we need to apply over here. I need a converter once again from Simulink to PS, and now I can attach it over here. And in the settings, I can say that this is torque, so I've set the unit to Newton meter. Okay, that's great. Now for energy calculations, I can use this function, and I'm going to copy these things over here. I have to provide theta dot, which is coming from here, and theta, which is coming from here. So I guess we have done everything. We haven't set the values over here. So for inertia, the value would be, because it is a point mass, so inertia will be m. So I've written m over here. For damper, the damping constant would be b. Currently b is 0.4, and all other things are set. Okay, to run this thing, you always have to attach a solver configuration block with the Simscape model. You can attach it anywhere. So I've attached it over here. You can attach it over here or anywhere else. Uh, okay, before running, I'm not logging this signal, but let me log it as well. So now I'm logging this theta signal and these energies. Okay, let me comment these out so that we only have this thing. Okay, that's it. So in the data inspector, we are seeing a flat line because we haven't given any initial angle to our pendulum. For initial angle, we can go to this ideal motion sensor and change the initial angle over here. So I can type in once again 0.5 radians and now run it once again. Okay, so in data inspector, we can see the oscillations, but I guess it is not like what we have seen earlier, because earlier we saw that at around 6 seconds, the oscillations completely died out. But over here, the things are still going on. I guess we have made some mistake. Let me go back and Yes, I have entered inertia as m, whereas although it is a point mass, it won't have any inertia around its own axis. But since pendulum is rotating about a fixed pivot point, which is L units away, so inertia of this pendulum bob around the axis of the pendulum, which is L units away, is not m, it will be m into L square. So I have to do that. So I've written that ml square, and now once again, let me run it. And yes, we can see the same results once again. Okay, so dear learners, you can see that we have modeled the pendulum using another kind of method, but we are seeing the same kind of results. Now let's move on to the third kind of method using multi-body elements. So let me go this side of the canvas. And for the multi-body, you have to insert the mechanism configuration. You have to insert the world frame, and you have to insert the solver configuration. So these three blocks are must for any multibody. In the mechanism configuration, I'm going to define this gravity as G because I have already defined it. And you don't have to change anything else. Okay, so from the world frame, the very first thing is I need to attach a revolute joint. But for the revolute joint, it always rotates about z-axis. So to make our animation uh, a bit more logical, I need to make sure that the z-axis is facing towards me. By default, the z-axis is facing upwards and x-axis is facing towards the right. So if I can rotate about the x-axis by 90 degree, I can make the z-axis come towards me. So I need a rigid transform. I can attach it with the world frame. I can attach this mechanism configuration and solver configuration anywhere to the model, but let me attach it at the very start. From this rigid transform, I need a rotation about x-axis of 90 degrees. Now my z-axis will be pointing outwards. I can attach a revolute joint over here. Okay, so this is my revolute joint. And now my z-axis is pointing outwards. You can run this model right now to see where the x's are. Okay, so let me do that. Let me comment this thing out and run this thing. Okay, so currently there is nothing. So in the Mechanics Explorer, you can click on the world frame. You can see the world frame is over here. By default, z-axis is going upwards, x-axis is going towards the right, and y-axis is going into the screen. But after rigid transform, you can see that now if I can rotate it a bit, you can see that z-axis is coming out, x-axis is going towards right, and y is going upwards. And we have the revolute joint over here. That's it. Okay, now I want to attach a rod with this revolute joint that goes downwards, and then at the end of the rod I have to attach pendulum bob. And now let's go back to our canvas and attach a rod over here, which can be inserted using a solid brick or brick solid. Now if I attach this brick solid directly with the joint, the center of this solid will be attached with this joint. So I have to displace the center downwards by half the length of this brick. Okay, so I need this rigid transform once again. And in this rigid transform, I don't need any rotation. I need a translation about standard axis, which is x. You can choose plus y or minus y. I'm choosing minus y, and the offset will be L by 2. I have to move downwards by half the length of the rod. So the length of the rod was L, and the downward axis is minus y axis, and that's why I've written minus L by 2 over here. And now over here, uh, I have to extend this thing in y-axis. So the y-axis dimension will be L, whereas z and x-axis can be any small dimension to show the massless rod. So I've chosen 0.005 like this, and I can click on this update, and this is the rod which I have modeled. For it to be massless rod so that it doesn't affect any movement of our pendulum, I need to define it as point mass, and then its weight will be 0. Okay, so that's it. You can change its color from the graphics tab, but for the time being, let it be. Okay, now we have the rod, and at the end of the rod, we want to attach the pendulum bob. Now to go to the end of the rod, we can use this transformation once again. And now this F part, the follower part, has moved L by 2 downwards again. So now we will be at the end of the rod. And over here, I can attach a spherical solid. This will represent our pendulum bob. You can change its radius to be anything, maybe 2.05. It is not important because because the important thing is the inertia. And in the inertia, I can go to point mass once again, and its mass will be m because we have already defined it. And now let me change its graphic as well, and let me make it a bit purple. So this is this pendulum bob which I have modeled. Okay, so press OK, and that's it. So we have modeled the pendulum, and we don't have to do anything else. All we now need is we need to provide some initial angle and then measure some things to figure out the kinetic and potential velocities. For that, I need to measure the position and velocity of this revolute joint. So I have turned on the sensing of position and velocity. Currently, the damping constant is 0. I can set it to be B. And for initial angle, I can go to this state targets, specify position target, and for radians, we can set 0.5. That's it. We have set all the parameters over here. Now using once again the converters, the PS to Simulink converters, I can convert these two signals, and I can once again use this energy calculation block. Okay, so I have provided once again theta dot and theta to this energy calculation function, and I want to record this theta as well. I've turned on the logging signal over here. Yeah, I guess that's it. I can run this thing, and you can go to the Mechanics Explorer, change its view to front view, and you can click on run, and you can see that the pendulum is moving, but it's moving quite slow. I guess I have entered the damping value a bit wrong. Okay, so I'm going to go back over here in the damping. Okay, the units over here are wrong. It's not degree per second, it's radians per second. So I can choose these units. Now it should be fine. Okay, so now you can see that the pendulum is oscillating, but at around 6 seconds, it almost stopped oscillating. So you can see that at 6 seconds, just about now, the oscillations have died out. Now let us go to this data inspector and see the results over here. And once again, you can see the oscillations, and over here the total energy is like this. Okay, so dear learners, you have seen three different methods of modeling the same simple pendulum. And in the last method of multibody, you can also see the animation, whereas all other results, they were present in the other methods of the Simscape and modeling the differential equation. So dear learners, I hope you have understood that how you can use these three different domains of modeling to model simple systems. In the next video, we are going to attach this pendulum with a card, and we are going to see that how the movement of this pendulum affects a freely sliding card. And later on, in future videos, we are going to attach a controller with the card so that we can maintain the angle of this pendulum to some inverted angle about the card. So that's all from my side. Stay safe and take care.